Hey everyone, welcome back. So you might have probably heard terms like DFT-s OFDM, cyclic prefix OFDM thrown around in 5G and 6G discussions. And if you have ever looked them up, you might have probably hit a wall of acronyms and math that made your eyes glaze over. Here is the thing. The actual story behind these waveforms is not that complicated. And if you understand that, then you would have a much clearer understanding of why 4G, 5G, and 6G physical layer signals behave the way they do. So in this video, we are going to break down the waveform evolution from LTE to 5G NR to 6G. Just the concepts that you actually need. Now let us get on to it. We are covering today. We will start with the why. Why do waveforms matter at all and what the key trade-offs are? Then we will go deep into 4G LTE, specifically two waveforms that it uses. There is cyclic prefix OFDM on the downlink and SC-FDMA or single carrier FDMA, otherwise known as DFT-s OFDM in the uplink. After that, we will have a look at 5G NR where things get more flexible. The uplink especially gets a big upgrade. Then we will peek at 6G, which isn't standardized yet actually. So at the time of recording this video, 6G release 20 standardization is ongoing, but we know quite a bit about where it is heading. And then we will wrap around with a side-by-side comparison table across all three generations. If you're here for a specific sections, timestamp are in the description, but I'd recommend watching it in the order. So each section actually builds on the previous. All right, now let us start with the fundamentals. So what even is a waveform? A waveform is essentially a mathematical blueprint for how you take your bits, your ones and zeros, and then turn them into a radio signal that can be propagated wirelessly over the air. And the choice of waveform is one of the most consequential decisions a standardization body like 3GPP makes because it directly affects the spectral efficiency, that is, how efficient you use the spectrum. Secondly, how much you put on the power amplifier in the device, in your UE, in your mobile phone. So that's the peak to average power ratio. We'll come back to this quite a lot. Reflections and echoes in real world. That's the multipath robustness. And finally, how much overhead does the system manage, does the system waste in just managing the waveform itself? That's like cyclic prefix, which again we will come back to quite a lot. Now, ITU and 3GPP loves their acronyms, but here is the thing, the waveform stories at its core is actually quite simple, and that's exactly what this video is going to be about. Before we go into deep, give the big picture, that is the evolution at a glance. We have three generations here, that is LTE starting from around 3GPP release 8 in 2008, then 5G NR from 3GPP release 15 in 2018, and then 6G, which we are expecting to be deployed by around 2029. As mentioned earlier, 6G release 20 task group discussions and standardization body researches are ongoing. Now, the base station to the user equipment or to your mobile phone. Do you notice something? All three stations uses cyclic prefix OFDM. That is the downlink waveform stable since LTE. We will explain this shortly. The uplink is where the things have evolved. LTE uses DFT-s OFDM. This is also called as SC-FDMA. 5G opened up the choice between DFT-s OFDM and cyclic prefix OFDM. 6G is heading towards something called as FDSS based DFT-s OFDM alongside cyclic prefix OFDM. We go through the details. It will all make sense by the end. Okay. Now, go into the fundamentals. Before OFDM, wireless systems used what's called a single carrier approach. Imagine you have a 10 megahertz channel. In a single carrier system, one carrier occupies the entire 10 megahertz. Now, to carry high data rates, your symbols have to be very short in time. And here is the problem. The real world is actually full of multipaths. Your signal can bounce off buildings, walls, cars, and then there is also multiple delayed copies of the same signal which can arrive at the receiver at slightly different times. If your symbols are very short for a high bandwidth part, so for higher data rates, the symbols have to be very short, then it is possible that these delayed echoes spill over to the next symbol. And this causes something called as inter-symbol interference or ISI. Dealing with ISI requires very complex receivers or equalizers at the receiver. Now, here is what OFDM does. So instead of wide carrier, it splits the bandwidth into hundreds or even thousands of narrow subcarriers, as you can see in this figure. So in LTE, the subcarrier spacing is fixed to 15 kilohertz. So this means that if the channel bandwidth is 10 megahertz, then it has like around 600 subcarriers. Each carrier carries symbols that are now much longer in time because the subcarrier spacing is narrow. This means that longer subcarriers are much more helpful to tolerate multipath delay spread. Now here is the elegant part. These subcarriers, as you can see in the figure, overlap in the frequency domain. That is, they are tightly packed together, but they are orthogonal to each other. This means that at the point where you sample each subcarrier, all the others are at zero. So you can perfectly separate them at the receiver. The result is that instead of one complex equalizer across a wide band, you just do one simple multiplication per subcarrier. This is a much cleaner approach. So this is a key takeaway from this slide. OFDM converts a wide band frequency selective channel into many flat narrowband subchannels. Okay, so now we understand why OFDM was required. Now let us talk about the specific flavor of OFDM that 4G LTE onwards use. This is the cyclic prefix OFDM. So CP stands for cyclic prefix. This is a critically important concept. So even with OFDM, multipath echoes can still cause problems. Specifically, they can cause intra-symbol interference between consecutive OFDM symbols. So this can totally destroy the orthogonality between subcarriers. The fix is kind of elegant. Before transmitting each OFDM symbol, you take a copy of the end of the symbol and then you stick it at the beginning. So that copy is called a cyclic prefix. So the structure actually looks like this. You have the cyclic prefix on the left, which is a copy of the tail symbol. You copy the symbol's tail and then you paste it to the beginning of the symbol. So this is, okay, so this means that this section is the fully useful OFDM symbol data, and whatever you have in the beginning is just a copy of the tail. So when the signal travels through the channel and arrives at the receiver with multipath echoes, as long as these echoes fit within the cyclic prefix duration, they don't touch the useful symbol at all. So the FFT at the receiver sees a clear circular convolution and then the subcarriers all stay orthogonal. CP give you. The CP, the cyclic prefix, protects the useful symbol from intra-symbol interference. It maintains subcarrier orthogonality even after multipath. But there is a cost. The cyclic prefix actually carries no new data. So they are just pure overhead. And you're spending some of your radio resources on protection and not for transmitting useful payload. And CP also has a key constraint for it to prevent intra-symbol interference. The constraint is that the CP length must be greater than or equal to the maximum multipath delay spread of the channel. So the higher the delay spread, the larger will be the cyclic prefix. From release 8 LTE onwards, cyclic prefix OFDM has been the downlink waveform. And as we will see, it stayed that way all the way till 6G. Now, If cyclic prefix OFDM is so great, why didn't LTE use it for uplink as well? The reason is PAPR, or peak to average power ratio. Let me explain why this matters so much in the uplink. In the standard OFDM signal, you are adding together hundreds of subcarriers simultaneously. So each one has a random phase and amplitude. So when many of them happen to add up constructively at the same instant, you get a very high peak in a time domain signal. So that ratio of that peak power to the average power is the PAPR. So PAPR equal to peak power to average power. And in OFDM, this peak power to average power ratio can get quite high. Why does this matter to your phone specifically? So your power amplifier, which actually drives the antenna, needs to handle those peaks without clipping the signal. The only way to do that is to either back off the average power or to use a more expensive, less efficient amplifier. So backing off power means there is worse coverage, which means the signal won't reach that far. A more expensive amplifier means a more expensive phone and much worse battery life. Now for the base station, this is manageable, but for the UE, it's not. So this is why we have DFT-s OFDM. The idea behind DFT-s OFDM is simple. Before you transmit the normal OFDM subcarrier mapping, you first apply a discrete Fourier transform to a block of modulated symbols. So this DFT will spread each symbol across all the allocated subcarriers. The effect is that the single carrier signal in the time domain. The peaks are lower and then the waveform is more smoother. This means that the peak to average power ratio drops significantly. Now let us take a look at the advantages. The benefits in the uplink is obvious. Lower peak to average power ratio means that the UE power amplifier runs more efficiently. There is much better coverage at the cell edge. There is better battery life, and then all these matter enormously for your user equipment. But it has disadvantages. There is lower spectral efficiency compared to cyclic prefix OFDM. And also, frequency selective scheduling. That means the process of assigning different users to the best subcarriers for their channel. This is even more harder. And there is DFT-s OFDM also limits to using contiguous subcarrier allocations, and then also using a single layer of MIMO. So MIMO is not that effective with DFT-s OFDM. This is exactly why LTE made a clear split. So there is CP-OFDM for downlink, where spectral efficiency is king, and DFT-s OFDM for uplink, where power efficiency is what matters. So let us put it all together for 4G LTE. So 3GPP Release 8, which came in around 2008, introduced this clean split. So in downlink uses CP-OFDM. Using OFDMA as a multiple access scheme just means that multiple users are served simultaneously. This means that each user gets a different set of subcarriers. In LTE, the resources are allocated in blocks of 12 subcarriers. They are called as resource blocks. So the scheduler at the base station assigns these resource blocks to the user based on their channel condition and service requirements. So the modulation in release 8 goes up to around 64 QAM, which means that each subcarrier gets around 6 bits per symbol. So LTE advanced in release 10 pushed that up to 256 QAM, which means that each subcarrier would get around 8 bits per symbol in the downlink. So in uplink, LTE uses SC-FDMA, otherwise known as DFT-s OFDM. Each user gets a single carrier-like signal. It has contiguous resource allocation with low PAPR. This is most beneficial for the UE power amplifier. Thus, LTE made a clean split. Cyclic CP-OFDM for downlink, which optimizes for spectral efficiency, and SC-FDMA for uplink, which optimizes for power efficiency for the user equipment. Now let us see what changed in 5G. Waveforms in 5G. 5G announced with 3GPP release 15 in 2018, and it kept cyclic prefix OFDM in the downlink. So there is no surprise in the downlink. But there is one massive upgrade, which is a scalable numerology. In LTE, the subcarrier spacing was fixed at 15 kilohertz no matter where the operation region was. In 5G NR, actually provided two regions of operations. There is FR1 and FR2. The channel conditions and requirements and the use cases required in these two frequency regions were entirely different. So 5G NR offered a flexible subcarrier spacing option. So based on the requirements, 15, 30, 60, 120 or 240 kilohertz subcarrier spacing can be chosen. We will look at why this matters in a moment, but then the short version is that the different frequency bands and different use cases needed different subcarrier spacing. So modulation is still up to 256 QAM in the downlink for release 15. Now here is what changed in 5G. So the uplink. 5G introduced a field called as transform precoder or transform precoder indicator, which helps the base station to let the UE choose between the waveform that is to be used in the uplink, whether it is DFT-s OFDM or cyclic prefix OFDM dynamically. So the network can just send a DCI saying, hey UE, just use DFT-s OFDM for the next DCI, next uplink push PUSH that you are going to send because that is better for your use case. So this network could allocate this dynamically to the UE. The 5G uplink innovation, it enables flexibility. So the UE is no longer locked into using a single waveform for all uplink scenarios. Now let us detour to understand this scalable numerology because it directly affects how cyclic prefix or FDM is deployed across 5G scenario. So each row here is a different numerology indexed by the Greek letter mu. So mu 0 is 15 kilohertz subcarrier spacing. That is your LTE equivalent numerology for sub 6 gigahertz cells. So mu 3 is 120 kilohertz. This is used for millimeter wave bands like 28 gigahertz or FR2 regions. Look at how the slow duration has when you double the subcarrier spacing. So 15 kilohertz subcarrier spacing has a slow duration of 1 millisecond, 30 kilohertz subcarrier spacing has a slow duration of 0.5 milliseconds, and so on and so forth. Now here is the waveform connection. So wider subcarrier spacing means that the OFDM symbol duration is shorter. Shorter symbol means that they need a shorter cyclic prefix to be effective. And shorter cyclic prefix is fine at millimeter wave because those channels have a small delay spread. So signal don't travel far enough to create big multipath echoes. But they do have Doppler spread because moving at speed through a millimeter wave beam is challenging. On the other hand, at lower frequencies like 700 megahertz covering a rural cell or an urban cell, you want longer symbols or longer with long wide cyclic prefix to combat for this delay spread. So conversely, you also need a smaller cyclic prefix to handle the large delay spread. So one waveform engine, the cyclic prefix OFDM, can be tuned differently for different scenarios. Now look how amazing is this. Disclaimer. At the time of making this video, 3GPP release training is not yet published. The task group discussions are still ongoing. The first 6G release is not published. So what I'm covering here is based on task group discussions, study items, and published research papers. The direction is kind of clear, but then details will have to slowly evolve. Now, the downlink waveform in 6G will be again cyclic prefix OFDM. There are no surprises here. It's well understood, it's flexible, it can scale for higher frequencies. Now, the 6G enhancements will be around AI-assisted channel estimation, then there will be higher subcarrier spacing probably for terahertz band, and then there will be tight integration with ISAC, integrated sensing and communication. Now, uplink. This is where 6G brings something new. The leading candidate in 6G for uplink is FDSS based DFT-s OFDM. So, FDSS stands for Frequency Domain Spectral Shaping. We'll go deeper into this in the next slide, but the key point here is that this is just DFT-s OFDM, but with an extra waveform shaping, which is much more optimized for reducing PAPR and out of band emissions. So CP-OFDM remains a candidate for some uplink scenarios as well. The flexibility principle from 5G carries forwards. Now I should mention OTFS, which is orthogonal time frequency space, which was a candidate waveform as well. This was heavily discussed. This was a heavily discussed 6G waveform candidate for quite a while. The idea was to operate in the delay Doppler domain rather than the time frequency domain, giving you better robustness to high Doppler and potentially lower cyclic prefix overhead. But then 3GPP task group discussions are more moving forward towards using FDSS based DFT-s OFDM in the uplink. Now let us go deeper into FDSS because it's the genuinely new thing in 6G. Frequency domain spectral shaping. The idea is that DFT spread step in DFT-s OFDM, you apply a filter in the frequency domain to spread the symbols before mapping into the subcarriers and before the IF50 stage. So the filter kind of shapes the spectrum. You are essentially windowing the signal in the frequency domain to smoothen the edges. Now look at the chain here. The standard DFT-s OFDM goes, and then there is a FDSS filter, there is a subcarrier mapping, and IF50 is done, and then cyclic prefix is added, and then so FDSS is just an extra step here. So this is added in between the DFT-s or DFT step, and then there is a subcarrier mapping. So this is a relatively small addition to an existing transmitter chain. So why does this matter so much for 6G? The answer is terahertz. So one of the major proposed use cases for 6G is communicating in the sub-terahertz and terahertz frequency bands. So we are talking about 100 gigahertz to like 1 terahertz. And there is also this favorite 6G band of around 7 gigahertz. The problem is that the power amplifiers at this terahertz frequency regions are extremely non-linear. So they are operating at the edge of what the semiconductor physics could allow. And non-linear amplifiers are much more sensitive to PAPR. So a high PAPR signal going into a non-linear terahertz amplifier can cause severe distortion to the signal. So FDSS, researchers suggest that FDSS significantly reduces the PAPR compared to plain DFT-s OFDM. It also reduces out-of-band emissions. Are converging on it. It's not a dramatic paradigm shift like when OFDM was introduced in 4G, but it's a carefully treated upgrade to reduce PAPR. Alright, now let us bring it all together in a single table. In downlink, CP-OFDM is used across all three generations. LTE uses it with OFDM, 5G added scalable numerology, now 6G will further enhance it to terahertz. So OFDM is a stable choice across all three generations ever since 4G. Now uplink is where the evolution has happened. LTE uses DFT-s OFDM via single carrier FDMA, then 5G offers a choice between DFT-s OFDM or cyclic prefix OFDM. This is flexible here. Now 6G introduces FDSS based DFT-s OFDM or cyclic prefix OFDM. This is ready for terahertz. The uplink benefit story actually tells the story much more clearly. So LTE prioritized low PAPR and battery life. Now 5G opened up the PAPR versus capacity or throughput trade-off. So 6G keeps on pushing down the PAPR with FDSS, which further reduces PAPR and also targeting on out-of-band emissions. Now, modulation peak in the downlink has gone from 256 QAM in LTE release 10 towards 1024 QAM in the proposed 6G specs. So 1024 QAM is like 10 bits per symbol, and higher modulation requires much better signal quality and channel estimation. This is another reason why AI assisted receivers are a key thing in 6G. And the release timeline. So LTE release was from release 8 towards release 17, onward, and then onwards going 5G NR releases from release 15, and release 20 onwards is 6G. Things for you to take away from this video. First one, cyclic prefix OFDM is the universal downlink waveform. It has been the answer since LTE and it is staying that way. The cyclic prefix elegantly solves a multi-path problem, the inter-symbol interference issues, and then the OFDM framework gives you a flexible, spectrally efficient multi-user scheduling. Then second, DFT-s OFDM is the by default low PAPR uplink choice. The DFT spreading step is the key. So what it does is it creates a single carrier like signal which helps reducing the average peak to average power ratio, and this is much beneficial for uplink user equipment. The third, the biggest innovation in 5G in uplink was flexibility. So the transform precoder lets the network to dynamically choose between DFT-s OFDM and cyclic prefix OFDM per user. So you can use low PAPR when it needs coverage and cyclic prefix OFDM when for higher capacity or for MIMO. And four, so the 6G upgrade in uplink is FDSS. FDS usage of frequency domain spectral shapers or extra filters right after the DFT stage to further reduce PAPR. And that's the waveform story from 4G to 5G to 6G. So I have dropped a couple of references on the screen for anybody who wants to dive deep into these waveforms. And so if you found this useful, please do hit the like button. It kind of helps this sort of technical content reach a broader audience. So if you have questions, feel free to drop them in the comments. I read everything. Next up, so I'm going to look into the actual modulation schemes that have been used from LTE onwards. So BPSK, QPSK, 256 QAM up to 1084 QAM, and where 6G is heading. So subscribe if you don't want to miss it. Thanks for watching, and I'll see you in the next video. Bye-bye.